Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Pleased to have Andrei Rybalchenko here from Max Planck Institute in Saarbrücken. He's a student of Andreas Podelsky, and he has been working for the past few years in using abstract interpretation-based techniques to prove liveness properties of programs using transition invariants, and that's what he will talk about today.
Thank you. So, hello and welcome. And yeah, I'm going to talk about transition invariants, and as you see, it's joint work with Andreas. So, what is the context? We're going to verify concurrent programs. And when we mean concurrent programs, these are huge infinite state systems, and there are different issues that arise in that context. And we're going to talk about deductive methods for verifying these programs. So what deductive methods means, it means that first you reduce temporal reasoning about infinite sequences of program states to first-order reasoning about assertions that describe sets of states, or maybe ranking functions. And a deductive proof rule is usually a set of some premises which says, okay, identify some assertions, then prove first-order validities between them, and then you are fine, then you prove the property. And usually it's quite difficult to find out those auxiliary assertions. In particular, ranking functions are notoriously difficult to automate. And what we are going to present is this new kind of auxiliary assertions for the temporal verification, which is suitable for automation via abstract interpretation. And I'm going to explain what transition invariants are. Then I show you a proof rule that applies transition invariants as auxiliary assertions, and I'm going to explain you how we obtain them via abstract interpretation. So first, let's look at some programs and remind you what are the issues that arise in the context of concurrency. So first of all, it's, of course, fairness. So if you look at this program, then it doesn't terminate if you assume any possible interleavings between the processes. It only terminates if the second process, the process B, eventually gets scheduled and sets the flag to true. And when it sets it to true, then the first process stops counting up the variable y, and eventually y goes down, and the whole system stops. Yeah, and you see that you cannot fix a priori the number of steps that this program is going to do, because it's really unbounded. This program may count to any positive number in the value y. Yeah, was the first issue, fairness. And in this example, fairness is even more intricate, and the interplay between fairness and ranking functions is even more complicated, because in the first place, this program is fully symmetric. Yeah, and what it does, it only modifies the value of the program variables where there is a context switch from one process to another. And if you assume that you start with some values, then whenever there is a context switch, the process takes the variable of the other process and sets to its own variable -1. And if that process continues running, then nothing happens until another context switch happens, and the values are really going like this. Yeah, and yeah, the main question is how to incorporate all these things into one proof rule, and such that there will be no notoriously difficult interplay between ranks and assertions. Yeah.
What's the property I'm thinking of here? Just termination?
Yeah, just termination. So the simplest liveness property you can think of, but that's actually the main liveness property. But what you want to prove.
Here are these assignments at the end.
No, the trick here are the assignments in the while loop.
Oh,
you see.
What are the assignments at the end doing then? Why are they there?
The assignments in the end assure you that if one variable goes to 0, then immediately the variable for the other process will also go to 0, and the whole system stops.
Will then terminate. I see.
And what you see here is really only if there is a context switch, then the evaluation change.
Yes. So you need a fair schedule. That schedules each one infinitely often.
Yeah, in particular, you need a failure schedule which is with strong fairness.
Strong fairness, transition fairness. Well, yeah.
Yeah. Okay. So that's another issue. And the last issue, which appears everywhere when you prove termination, is the synthesis of ranking function. For example, for this program, its termination doesn't really require any fairness assumptions. But to come up with a ranking function is it's difficult, believe me. And you may say, okay, it's something like I could encode in terminal write system and then apply all the techniques for terminal writing, and or maybe come up with some lexicographic ordering. And we tried all the tools, or all the tools that are available on the web to prove termination by encoding to TRS. And we need polynomial interpretation for the symbols appearing in the TRS. And if you encode them back to in terms of program variables, then you require ranking functions that involve exponential equations over program variables. And yeah, that's the third issue that arises in temporal verification. So namely, synthesis of ranking functions, which is difficult. So we have fairness in ranking functions, and transition variants are going to help us to move these things smoothly together. So what is a transition invariant? So you can think of it as a superset of the transitive closure of the transition relation of the program. So you may think of a program as denoting relation between current state and the successor state. And you take that relation, put plus over there, and any over-approximation of that would be a transition variant. And if you look at it formally, it would look like this. And if you want to account for the initial states of the program, you're going to say, okay, I have some description of the accessible states of the program, and then I strengthen the transitive closure by intersecting it with the accessible states. And that's the definition for transition invariance. And now I'm going to show you the connection to state invariance, so to provide some intuition. So you see that transition invariance contains all pairs of states where the first step jumps to the second step after some arbitrary number of program steps. Yeah? And this gives you a way to connect state invariance and transition invariance. Namely, if you take a transition invariance, fix the first states of the relation to the initial states of the program, yeah, and then project the relation to the successor states, then you obtain all states that are reachable in the program. That's what's written here. Yeah? So now we have transition invariance, and we need a property which allows us to reason about temporal properties. And this property appears to be disjunctive well-foundedness. Actually, this property is completely independent from programs. It's a property about relations. And what it says is that if you have a relation, and you can partition it into finite number, and finiteness here is really crucial, into finite number of well-founded relations, then you can call the original relation disjunctively well-founded. Yeah, and what is important here is that disjunctive well-foundedness is not something stronger than well-foundedness. So you can have disjunctively well-founded relations which are not well-founded. For example, this one. If you have a relation which contains two elements, acknowledge goes to request and back. So obviously, each of the components here are well-founded. In those relations, you can only do one step. Yeah, but if you put them together, then you can go from egg to rec and then back to egg. So the union is not well-founded. And another interesting property is that because of the first one, also all the sub-relations of a disjunctive well-founded relation are not necessarily well-founded. So if R subset of T, then you cannot really say anything about R. But if R plus is a subset of T, then you can conclude well-foundedness, and that's what it's all about. So now let's show me the transition invariant of yeah.
Can you show me the last time?
Yeah.
So what is it? R plus is a subset of T.
Yeah. So if T is a transition invariant for R, yeah, and T is disjunctively well-founded, then R is also well-founded. But you need to have R plus, not only R, this subset of T.
Why is that?
Yeah, that's the whole issue of transition invariance.
But you can prove that.
Yeah. Okay. Now let's see how the transition invariants look like. For example, for this program, you can classify all intermediate jumps in program computations. You know that if you start somewhere and go to some other states, that either you are going to change the program location of the second process. This is this component here. So you're doing some step in the process B. Or you doing some location change in the first process. Or maybe you are looping in the first process in one of those loops. And when you loop there, then either y goes down, which is the second loop at location L2, or you're looping in the first process, and you know that t is true, and x stays the same. And obviously you can see that this relation, the union of these t's, is disjunctively well-founded, almost. So you see the last two relations are well-founded because you can only make one step in those relations. Yeah, the first relation is well-founded because you pushing y down, y is strictly decreasing at each step, and it's bounded from below by 0.
Actually, there's an issue that I've had about this in the paper. So when you say PCA does not equal PC prime A,
yeah.
Those are ranging over 4 labels, right?
Yeah.
So really what you're really saying is T3 is a shorthand for actually a number of other.
Yeah, that's true.
Because if you actually make that relation, it will have a cycle in it.
Yeah, that's true.
Right.
That's a shorthand notation for big disjunction over all pairs of different program locations.
But this was actually quite a point of confusion for me in the paper. That when you're quantifying over these labels, you really are, T3 is really a shorthand for a set of a finite set of things, because T3 really itself is not well-founded.
Yeah,
if you literally
you go
take
from
that as,
1 to 2 and from 2 to 1.
right, you go from 1 to 2 and 2 to 1. But the point is, since there are a finite number of labels, you can break them up so that you don't have these cycles.
Yeah,
and that, I just wanted to let you know that confused me. That confused me for quite a while until I realized that it was a shorthand.
Okay, thank you. Okay, that was a transition variant for a program. Yeah, and it's almost disjunctively well-founded in the sense that all but the second subrelation is well-founded. And the second subrelation is actually denoting a jumps where the second process is not executed between those jumps. So you see axis remains true. It means that the second process is not scheduled. And obviously it is something which we don't want to consider because it represents an unfair sequence of jumps where the second process is never executed. Although we would assume that in any fair executions it won't be the case. Yeah. So now let's do a verification. And we're going to apply the Automata-theoretic approach to verification, where we uniformly treat Liveness properties and temporal properties and fairness assumptions as sequences, infinite sequences over states. And what we're going to do, first we're going to construct some program which will reflect the original program under consideration and somehow incorporate the property that we want to verify. And then we're going to prove, as a second step, that this program is in fact fairly terminating. And how are we going to do that? So we take a Bush automaton that accepts all infinite executions of the program that satisfy the fairness assumptions but violate the property. And then we take the synchronous parallel composition of the program with that automaton, which would act as a monitor, restricting the program behaviors to those that are fair but violate the property. And what we're going to do then, we apply Vardy's theorem, and we just prove fair termination of that product. And how are we going to apply transition invariance in this case? It's like this. So assume we have a program, assume we have a parallel product of the program with the property automaton, and our theorem is like this. So we're going to come up with a transition invariant for the product, which is disjunctively well-founded if you restrict it to fair states of the product. By fair state, you may assume that the specification automaton is equipped with the Bush accepting conditions. And when you compose it together with the program, you obtain fairness requirements in terms of Bush accepting conditions. So you have some set of states, and you require that this set must be visited infinitely many often during all fair computations. Yeah, and then you intersect it with a relation. And if you prove that that relation is in fact, disjunctively well-founded transition invariants, then you are done. Let's show me briefly how it works. So first, we're doing the proof by contradiction. We assume that all the premises of the theorem hold, and there is some fair infinite computation. Yeah. And what we're going to prove is that one of the subrelations in the transition invariant is in fact not well-founded. Yeah. So first we look at the sequence and pick a subsequence, infinite subsequence, that goes from one fair state to another. And since we assume that the computation is fair and infinite, then there exists such an infinite subsequence. Yeah. Then we define an equivalence relation on the positions from that subsequence. And we say we pick a pair of states, and we know that each pair of states from that subsequence is an element of one of the components of the transition relation. Yeah? And we say, okay, two pairs are equivalent if they are mapped to the same subrelation.
This is really important. This is why R plus the transitive closure of the program's transition relation must be in T. Because if that weren't the case, then this would not hold.
Yeah.
Because you need to take any pair in that infinite sequence, any pair of states, no matter how far apart.
Yeah.
And you want them to map to a TI. And if the T wasn't a transition invariant, then you wouldn't be able to. Then this equivalence relation would not be total.
Yeah, you're completely right. So the fact that T is a transition invariant proves us existence of such equivalence relation, which is, as you said, total. Yeah. So what we have now, we have an infinite error trace. Not an error trace. We have an infinite fair computation. We took a subsequence. We mapped elements from that subsequence to the subrelations of the transition invariant. And we obtained an equivalence relation with finite index. Yeah. And now we can apply Ramsey theorem, which says, okay, if you have such an equivalence relation with a finite index, there must be some subsequence of the original subsequence. So that's the subsequence of the second order, where it doesn't matter which two pairs of states you pick. They are all mapped to the very same a priori fixed element of the transition relation. It means that they are all in the same equivalence class. Yeah. And what does really mean is that you have some fixed components, some fixed subrelation of the transition invariant, and you have infinite sequence of pairs where one state jumps to the other and jumps to another, and all of them are elements of that relation. And this means that the relation that denotes the equivalence class is not well-founded. And this is a contradiction to our assumption that the transition invariant was disjunctively well-founded. And that concludes the theorem. So that was the if part, which says that if you have transition invariant is disjunctively well-founded after the restriction to fair states, then property still holds. So we have fair termination. And the other direction is fairly simple, which says that our theorem is, in a sense, complete. Yeah. So the other question is, okay, we have this theorem which says if you want to prove Liveness property or temporal properties, then take the automata for the property, compose it with a program, then take transition invariant for that, and if you manage to prove it's disjunctively well-founded, you are done. But it doesn't say how you're going to identify whether a relation that you are looking at is transition invariant or not, because we haven't identified some effective means to do that. And the way how we're going to do that is introduce some inductiveness principle for transition invariance. And we say, okay, some relation is inductive if it contains the transition relation of the program, the first line there, and it also closed under the relational composition with the transition relation of the program. So it's like inductiveness for state invariance. So you say the state invariant is something which is over-approximation of the initial states of the program, and it must also be closed out under the next operator of the program. So whenever you do a next, then you'll be in the subrelation of the inductive invariant. And that is here, but lifted to relations. And you may account for the accessible states. That is written in gray. Yeah. And there are some observations about inductive relations. First of all, it's easy to see that an inductive relation is a transition invariant. So it's immediate to prove by induction of the length of the sequence that you're considering, where you want to map the first and the last stage from the sequence to the transition invariant. It also says that inductive relations are not necessarily transitive. So if you compose two inductive relations, you're not necessarily going to obtain a subset of the relation. But another curious thing about the inductiveness is that if you have, what I said before is that disjunctive well-foundedness doesn't imply well-foundedness. But if you have a relation which is disjunctively well-founded and inductive, means it's closed under the composition with itself, then it's also well-founded. And the reason why is because you may see that any relation which is closed under the composition with itself is in fact a transition relation invariant for itself, because it's a superset of itself, and it's closed under the relational composition with itself. So it's inductive relation. Yeah, that's the reason for the first remark. Yeah. So we have inductiveness. We can identify transition invariants, so we can proceed to the proof rule, which will utilize transition invariants. So what do you have there? So assume we want to prove program, and we apply the first step of the automata-theoretic construction. There you have the program composed with a monitor. Yeah. Then we're going to say, okay, we look in some relation. And then we need to establish the three premises, three conditions, which the first two says, okay, the relation that we assume to be a transition invariant is in fact transition invariant, because we prove that it's inductive. And then we are going to establish that it's disjunctively well-founded, the condition that comes from the theorem. And if you manage to do all these things, then you're done, you prove the property. And this proof rule is sound and complete, so whenever the property holds, you're able to come up with a relation T which satisfies all three components, all three conditions. Yeah? And what does it mean, establish the premises of the proof rule? So the first two amounts to entailments checks. So usually one presents a program as a set of statements, and each statement denotes some relation. And you will also give a candidate for transition invariant as a set of relations. And then to prove that they're inductive, you will just do relational compositions by doing quantifier eliminations on the assertions that represent the relations. So basically you eliminate the intermediate variables when doing composition. And then you're doing entailment checks. The tricky part is how to establish the last condition. So you need to prove disjunctive well-foundedness by what it means. You're looking at all those small components and trying to apply all the methods you know to prove that they are terminating, that they are well-founded. And then you say, okay, what I gain from here? Yes, in the extreme case, when you say, okay, this huge thing without structure is my transition invariant, and I don't want to partition into components, then, yeah, you haven't gained anything. So it's quite difficult to prove that it's disjunctively well-founded. But if you manage to produce your transition invariant in such a way that is possibly a huge number of components, but each of them is well-structured, then you can apply efficient tools for proving the well-foundedness of the small components, but maybe you need to quite a huge number of such checks. And if you recall the example, there we see that each of the components of the transition invariant was represented by a conjunction, which you can see as a program of this particular kind. So you say, while some condition holds, do updates on the variables. It was like y greater 0 and y prime less than y. And we would allow updates here to be non-deterministic. Yeah. So, and now we are done. So we have a proof rule, for which we know how to identify the auxiliary assertions. We know how to establish the premises of the proof rule. And then most people from the deductive methodology would say, okay, and that's the creativity of the user of the proof rule to supply the transition invariants, the candidates. And we go further and say, okay, it appears to be quite difficult to come up with these transition invariants because they reason not only about program variables, but also about primed versions. So the assertions contain double number of variables. And you're not really going to scratch your head and come up with those formulas. You're going to synthesize them automatically. And how are we going to do that? So we say, okay, we're looking at those transition invariants that are inductive relations, in the sense that they are closed under the relational composition with the transition relation of the program. Yeah? And then we define an operator which takes some relation and composes it with the program. Yeah? And we can do approximations of that operator like you do in predicate abstraction for safety properties. So you apply an operator and obtain a result and then approximate by some given fixed collection of formulas or collection of relations. And you can easily see that the least fixed points of the approximation of the operator f, that they are transition invariants. And you can apply all the techniques you know for the verification of safety properties, where you compute least fixed points of the post operator to compute least fixed points of the operator f sharp. Because the only difference is that instead of instead of doing post, you're doing relational compositions, and your formulas now are not only over program variables, but also over the primed versions. Yeah. So let's look at this program, for which, if you do a ranking function, then you need some horrible exponential expression as the rank. So if you fix the following set of transition predicates, which come from linear arithmetic, and compute a transition invariant, so you compute the least fixed point of the operator f, and each time you compute the next values under those operator, you look at the bit vectors over those predicates and try to come up with the tightest over approximation. Then you obtain the transition invariant, which is union of the relation T1 to T4. And you see that to prove well-foundedness of each of them is quite easy. You can do it applying linear ranking functions. So you see that in all of the components, in the first one, x is going down. In the second, the sum of x and y is going down, and so on. Yeah? And that's basically all what I wanted to say about transition invariants. And what about the related work? You must say, okay, we have this huge deductive methodology, which says, okay, give me some assertions of a state space, and then give me a number of ranking functions. And there will be interplay between sets of states and ranking functions. But one of the most important difficulties by applying that methodology is that nobody really knows how to synthesize ranking functions automatically maybe by applying abstract interpretation. And you can do that with transition invariants. And another work that was actual inspiration for our work was that's the size change termination principle for functional programs. There you track size changes that appear in function parameters when you jump from one call site to another. Yeah, and then you can abstract those size changes as size changing graphs. That's a particular kind of abstraction, and then you compute closure over that graphs, and so you can prove termination. If you look at the abstract interpretation point of view, the difference is that our abstraction is parameterized, so our fixed point operator is in fact more precise than for this fixed abstraction, these size change graphs, which I can present as formulas like x, y less than z, which will say, okay, if I copy the parameter z to the parameter x, there's something must go down. And another difference is that we The first one is we apply parameterized abstraction, we account for liveness and fairness. Yeah, and about the ongoing and future work. So one thing is that you might don't want to do is to put all fairness requirements that you have for the program. There could be a huge number of them for each program transition to the specification automaton, because it will blow up the specification automaton and the product will be very big. So we are looking at ways how to account for this kind of fairness in the calculus. So we, yeah?
You might want to talk about that. So if you require strong fairness,
Yeah.
then there's a recent result that I have with Warnick-Kupperman that may be interesting to you.
Mm-hmm.
I don't know if it'll be applicable here, but it allows for a much more direct encoding of fairness.
Okay.
When you have strong fairness.
So in the first item, what we are looking at specification automata that have straight accepting conditions. And then we modify the calculus to account for that directly.
Okay.
So another thing is you can look at transition variants and see them as relational summaries. And those summaries will provide you the possibility to summarize some chunks of code like while loops or even whole procedures, and also account for liveness properties in those summaries. And the most recent application or extension of the idea of transition invariants is abstract transition programs. And these abstract transition programs are finite graphs. And the nodes from those graphs are labeled via bit vectors over transition predicates. And the edges in the graphs are labeled by program transitions. In looking at those abstract transition programs, you can reason about termination. You look at the nodes at the relation and their well-foundedness. And you can also directly reason about fairness assumptions that are imposed on the program transitions by looking at the edges that lead to particular nodes. In this way, you can account for deconstruct fairness assumptions in terms of program transitions, like no transition which is continuously enabled is not taken infinitely often or in the contrapositive. So every transition which is continuously enabled must be taken infinitely often, or every transition which is infinitely often enabled must be taken infinitely often. So we can prove fair termination with weak and strong fairness assumptions imposed on transitions. That's what abstract transition programs are about. Okay, thank you.
So how do you actually determine the finite disjunction? It wasn't so clear to me. How do you know how to break things up? Is that just clear from the structure of the program?
That comes from the fixed point iteration. If you look at...
So the fixed point iteration starts with the course partitioning and starts to divide it up? How does it work?
The fixed point iteration, it's pretty much like in safety. So you start with some initial state, and then you apply the post operator, and it produces you a big disjunction,
Sure.
over all application of program statements,
But it's too fine. Is that?
Yeah. No, in this case we do the same. We start with the transition relation of the program, and then we take each of the program transitions and compose, and then we obtain a set of successor relations.
Yes.
Yeah. And then for each of those successor relations, we again apply each of the program transitions.
That's right.
That's how we obtain a tree, and we obtain the partition into the components for free. And then we look at that partitioning and try to prove that each of the components is well-founded. You may.
So you're saying during the fixed point computation, you're really starting from initial states, just like you're doing reachability analysis, except you're computing a fixed point over not over states but over relations.
Yeah.
And then you're saying whatever the partitioning is that arises is the one you use.
Yeah. And in particular, that partition has structure which is induced by the transition predicate, by the abstraction that you use via. Because you know that you are only allowed to, for example, use bit vectors over transition predicates for the abstraction. So each time you apply a next relational composition step, you approximate a result by disjunction over bit vectors. That's how you obtain a disjunction. It keeps growing. And each of the disjuncts is represented by a bit vector, so it has a particular structure. So it is a conjunction of predicates that appear in the bit vector.
I understand. So how does this relate to the to the local analysis that Andreas and Georgia did, where you right. So the idea is you have a transition relation instead of applying the whole transition relation to a set of states. You do it locally.
Yeah, that's exactly the way it goes.
Okay.
So you have some intermediate status of your fixed point computation.
Yes.
It's a set of bit vectors. And you take each of the bit vectors and apply each of the programs alone.
So you do everything separately.
Yeah.
And that's sort of how you get these partitions.
Yeah.
I see. Because if you just sort of did it all at once, then it would not be so clear. But of course, you can do that symbolically, I guess, too, right? I mean, you can do the whole operation symbolically.
What you can also do is that, you can first abstract all the transitions of the program into transformers over bit vectors, where the bit vectors stand for transition predicates like lambdas. First abstract the...
but raised up to relations,
Yeah, and then you can compute this fixed point symbolically.
Sure.
That's also possible.
Sure. Okay.
When you say local, you meant in a concurrent process, you will take one process at a time, is what you meant by local.
Yeah. Actually, here you don't distinguish between transitions that are in different processes. You apply all of them. You don't distinguish.
But I imagine there would be many different ways to optimize, to make it work.
How are your results? I know that you've implemented some of these things. How do they work out for you?
Oh, the things they work out really nice. So far we applied them on the classical examples from Manapnelli books on temporal verification, like bakery and all these kinds of virtual queues and ticket. And what we see so far is that why we started this direct encoding of fairness, that when we take bakery program and then we look at the fairness assumption for bakery program, and you have about 10 fairness assumptions. And if you encode that, you express it via LTL formula, and then you apply LTL to BA or whatever to produce a Bush automaton. It gives you a huge automaton. And if you take that huge automaton and compose with the bakery program and start to compute over that really huge program, the transition invariant, then that takes a lot of time. Then when we switch to direct encoding, then it works fine. And if you say, okay, I don't have fairness and I only want to prove termination, then we looked at a bunch of C programs from the numerical recipes in C, and that worked fine. And all the predicates that we extract from the program code, like x goes up, x goes down, depending where x is incremented or not. And if you take those predicates from the text of the program, that in very many cases we are able to prove termination.
So basically what you're saying is that if you don't have, the explosion happens because of the composition of the property automaton. And if you don't have that, you are able to prove this without manual ranking functions. The automatic method just works, is what you're saying.
Yeah, because as you see, so you fix those predicates, and the components of the transition invariant will be bit vectors over the predicates, and they are really conjunctions of predicates, and for those programs it's easy to prove well-foundedness. Yeah, and even if the updates there in this simple program, simple while programs are deterministic, termination for those programs over reals is even decidable. So the main problem is to compute the fixed point, but that's where we see a lot of potential, because people know how to compute least fixed points and how to do abstraction for that case.
So really, to sort of summarize proof rule and the technique, really, the base problem is still determining whether a relation is well-founded. But what you've done is given a technique that allows us to decompose this hard problem over the program's transition relation into smaller subproblems.
Yeah.
But still, we have this base problem of finding these ranking functions.
Yeah.
Still, so it's really this idea of making all these tests sort of local.
Yeah.
And that's through this disjunction, right?
Yeah. So you can say, okay.
So there will be some hard problems that it may be very hard to find this sort of disjunction. But that's sort of, but at the bottom, there's still the same problem, which is sort of finding the ranking functions, proving that a relation is well-founded.
Yeah, I mean, if you want to prove Liveness properties, it's about well-foundedness.
Yes, of course.
Yeah, and then, of course, you may say, okay, maybe you can say, okay, we just put the problem from A to B. But, yeah, and you say, okay, my transition invariant, you just write R plus the transitive closure is my transition invariant. You say proof termination, they say, okay, I don't know. But if you come up with a nice partitioning, then you can do it. And the main idea here why this should work is that you can leave it to the computer to compute the partitioning, to compute the fixed point. And that's where computational power will help us.
But still there has to be some smarts in finding these ranking functions at the end. And then the other thing that your technique gives us is the ability to apply predicate abstraction. Because the transition invariant is an over-approximation of the transitive closure. Essentially, it provides a means for applying abstraction.
Yeah, because of the inductiveness. You have characterization of transition invariants as least fixed points.
Yes. Right.
And in fact, it doesn't matter where you have program variables and program variables and prime variables in the assertions. You just compute a fixed point. Yeah.
So, and suppose you apply one particular predicate abstraction on a program, you get your transition invariant, and then you find that one disjunct is not well-founded.
Yeah.
What do you do?
Then I say, okay, I look at the sequence of statements whose composition produced that particular disjunct. And then I can refine along that path. Then maybe you can see, okay, I'm looking at that path, yeah? And that path is a loop. And then you say, okay, look at that loop. And if it falls to the decidable class of the while loops, then you say, okay, it doesn't really terminate. Because it gives you a hint where the non-termination may reside in the program. It gives you the path through the control flow graph, which says, okay, along that path, if you go there, I cannot tell you anything.
So is the refinement procedure automatic? That's my next question.
That's what we are working on, but that would be the line along which we will go into the refinement. And you can also think about, in many cases, you cannot prove some temporal property because you don't have enough fairness assumptions. Yeah, and this will also give you a way, in particular in abstract transition programs. It may hint you, okay, this transition was in the loop, but somehow ignored. Maybe we need some fairness requirement for it.
Just a couple of questions. When you said the matrix protocol, you meant the matrix, or
yeah, of course.
And the other thing is, I think the inductive verification for really have something called distributed ranking rule. Have you looked into that?
Distributed rank. Is that for the parameterized systems?
Well, it applies to any system. But, so just like we have this deductive rule for safety properties,
Okay.
they have this distributed ranking rule for.
But for the distributed ranking rule, in the first place, you need to come up with a distributed ranking function. I mean, that's again a complete proof methodology.
Right.
Yeah, but they don't say how to come up with the distributed ranking function in the first place.
But you also give a sound and complete proof rule, right?
Yeah.
So, is there any relation between these two, or?
I mean, of course, you can take ranking function from one proof rule and transfer them to the ranking function of the other.
Thank you.
Great. Thank you very much.
Thank you.
Actually, Andre is listening for a couple of more weeks.